Alright, so today we're going to be talking about thrust. We're going to be using a lot of the terminology we've been using, and I'm just going to review the airfoil related terms. So hopefully we start getting more familiar with them. And we got to remember the propellers are airfoils. So you guys are going to learn that propellers have an inherent variability in thrust production due to the difference in velocity from blade root to tip. And we talked about this when we were actually in class. So you're actually going to use that lift formula that we talked about in the previous lecture, and understand how velocity changes over the length of the blade, and then we're going to use what we know about airfoil design. So you're going to be exploring how rotating propellers create four turning tendencies. These phenomena are called the corkscrew effect, the torque reaction, P factor, and gyroscopic force. And this is where we would be playing with those Littlewood airplanes if we were in class. And then we're also going to discuss more about jet engines and how they actually function. I know that was something that we had discussed was confusing earlier on. So we want to understand that a propeller is not some simple blade. There is a lot of engineering and designing that goes in to making these things. Alright, so this again is a review, but I just want to go over a few things. Lift is what pulls the airplane into the sky, created by wings on the airplane or rotor blades of a helicopter or drone. So by definition, it acts perpendicular to the relative wind or line of flight. Weight is the force of two masses being attracted to each other. It is the force that pulls objects towards the center of the earth and makes things fall down. Amazing definition, right? Thrust is created by the jet engines or propellers of a plane. Thrust is the push that moves the aircraft through the air. And drag is the resistance or friction to things moving through the air. It is caused by air particles bumping into the object. Rotating airfoils, and they're rotating in the vertical plane. So we need to understand that thrust is essentially lift that's being created in the direction of the flight. Alright, so and again, this is a review of everything we talked about. I know there's a lot of terminology, so I'm just going to go through all this stuff. So the leading edge is the first place air makes contact with the airfoil. The trailing edge is the last place air makes contact with the airfoil. The chord, it's an imaginary straight line connecting the lead and trailing edges of an airfoil. Relative wind, the direction of airflow relative to the wing when the wing is moving through the air. Relative wind always moves directly opposite the direction the aircraft is moving. Angle of attack is the angle between the chord line and the direction of the relative wind. Thickness, the point where the airfoil has the greatest height from top to bottom, expresses a fraction or percentage of the chord. Camber is the curvature of the airfoil and may be considered curvature of the mean camber line. So mean camber line is a line drawn between the leading edge and the trailing edge so that the distance between the upper and lower surfaces are equal. The maximum camber, the point on which the airfoil has the greatest distance between mean camber line and the chord line. Sure, we all remember that, right? Alright, so a propeller is a rotating airfoil that produces thrust by its action on the air direction perpendicular to the plane of rotation. Both propellers and wings are engineered with focus on leading and trailing edges, chord lines, angle attack, thickness, and camber. Alright, we've seen this a lot. Newton's third law. For propellers, we need to define that the action. We want to define the action and its equal and opposite reaction. So give it, think about that. So the action is the rotating propeller blades moving a large mass of air towards the rear of the aircraft. So reaction. An equal and opposite movement of the plane forward. Alright, so here's just a quick visual on how a propeller screws into the air, or takes a bite out of the air, however you want to think about it.
When moving through the air, it generates a total reaction, which enables an aircraft to fly. This is best explained by looking at it in terms of the lift produced by the aerofoil and the drag created by its resistance to the air. If the angle of attack is increased, more lift is generated, but at the expense of increased drag. Maximum lift being produced at the point of stall. A wing is usually at its most efficient at a relatively small angle of attack. In very simple terms, a propeller or air screw is really two or more rotating aerofoils set to pull the propeller through the air, in the same way as the thread of a screw pulls it into wood. During flight, its motion will comprise rotational velocity and forward velocity. With the propeller stationary, any forward velocity is that of the aircraft, the true airspeed. But a rotating propeller accelerates air and produces the induced flow. The sum of the TAS and the induced flow is the total inflow.
Alright, so of course we're not going to be able to do this activity, but if you're out somewhere where you can get a balsa plane, you should totally do this on your own. And like I said, if we get back to class before school's out, we're going to spend a week just doing all these projects that we didn't get to do. Alright. So this is just describing, how a propeller works. We don't really put much thought into it, but notice, everything moves together, obviously. It's one propeller, but they all have different velocities based on where they're located at. So you can look at the diagram there and see that, at the end, the blade has a greater distance to travel, and it has a very high speed compared to what is right in the center. Alright, so at this point you're going to have to grab your family, I guess, if you want to try this. So we need like 5 people to stand in the line shoulder to shoulder, and you're going to have to walk by rotating around the center point so you can see how a propeller works. Have fun with that. So, read these and think about an answer to this. So one of the things that we talked about was the elements of lift equation, that the variable velocities along the length of the propeller blade would create asymmetrical thrust. And varying velocity along the propeller would cause too little thrust at the root and too much at the tip. So this will put a bunch of pressure on the tip, distorting the blade and potentially bending or breaking it, which would obviously be bad. Alright, we've already seen this before, but I want to remind you guys that lift is proportional to velocity squared and the lift coefficient, which increases with increasing angle of attack. And remember, propellers are airfoils. Airfoils do produce lift, so we can use the lift formula here. However, we need to make sure to remember that the propeller's lift is produced in a forward direction, so we call that thrust. And hopefully from the previous video you remember that velocity is the factor that most affects lift. So because velocity in the equation is squared, faster moving airfoils generate exponentially more lift. Alright, so I just want to demonstrate how quickly variable velocity along a constant angle of attack propeller blade will cause thrust to build towards the tip of the propeller. Sorry, I can't talk today. So, and the coefficient of lift, density and surface area are held constant just square the velocity to determine the relative values. So if we look at the blade position at 10 inches, our velocity is 129. If we squared the velocity, we would have 16,641. If we squared the 20 inches, 259 knots, we'd be at 67,081. And if we, at the 30 inches, we'd have 398. If we squared that, we would have 158,404. So it kind of gives you a good idea of this exponential growth that we're talking about. And this just shows you the actual graph if we were to plot those points and connect the dot. And hopefully from your Algebra 2 class, you see that that does look like an exponential function. So you can also see that, you know, you have exponentially more thrust at the tip due to the greater velocity around here at 30 inches. So hopefully now we understand that each part of the propeller blade must be different in order to create the even thrust across the entire airfoil. So, think about solutions, creating symmetric or even thrust from root to tip, using what you know about the lift formula, and think about what factors could be varied in order to evenly distribute the thrust along the propeller blade. So you also need to remember that changing the camber and angle of attack changes the coefficient of lift. Alright, so I know you guys are already thinking about these answers. So you change the angle of attack so that is greater where the velocity is slow, which is more lift, and shallower where the velocity is high, less lift. Increase the camber at the root, so you have more lift, and decrease it at the tips, so it produces less lift. Change the surface area of the propeller, less area at the tips and more at the root to keep the velocity equal. All great ideas. Alright, so you can read these on your own, but these are things that engineers would do. Obviously, what we just talked about, changing the surface area, changing the camber, and changing the angle of attack. But again, a lot of thought and design goes into how a propeller is made. And we talked about this, I don't know, a couple weeks before we went to online schooling. So I'm not going to say much about this, but we can see how they fixed the uneven thrust problem by varying all those elements. So this is something else to be thinking about, that sometimes if you have a fixed wing propeller or fixed pitch propeller, you're not going to be able to adjust and maintain the most efficient angle of attack, and they're relating it to a single speed bicycle. Great example, right? If you ain't got those other gears, it's going to make life a lot more difficult for going up hills or building up speed to coast. So alright, so you can read through these on your own as well. But fixed pitch propellers with a low pitch are designed to be optimal for taking off and climbing. This type of propeller is known as a climb propeller. So you can see that right there. At lower pitch, the propeller handles a smaller amount of air for each revolution. Handling less air allows the engine to turn at a higher RPM. Higher RPM creates maximum thrust. But however, once the plane's cruising, the propeller will spin too quickly and is not able to push enough air during each revolution. So fixed pitch propellers with a high pitch are designed to be optimal for cruising. This type of propeller is known as a cruise propeller. At a higher blade angle, the propeller handles more air on each revolution, which causes the engine to turn at a lower RPM. Decreasing the engine RPM reduces fuel consumption, engine wear, while still keeping the thrust at a maximum. During takeoff and climb, the engine using a cruise propeller must work harder as it tries to rotate and produce enough thrust with such a high pitch. And here we are at the variable pitch. So, pretty self-explanatory. The pilot is able to change the pitch of the propeller for maximum efficiency. Alright, so we talked about this at the beginning of this. We are going to take a look at corkscrew effect, torque reaction, P factor, and gyroscopic action.
Hey everyone, Jason Schapper here of M0A.com. Today we're going to talk about some left-turning tendencies. So often we just call everything P factor. If it pulls us to the left, if it requires us to have some right rudder in there, we just call it P factor. But do you know that there's actually 4 types of left-turning tendencies that you're going to need to know and understand their subtle differences as well? Let's work through those 4 together here. The first, we'll start with the easiest, is P factor. Really, it's technically called asymmetric propeller loading, which says the following, which we've learned for so long. The descending propeller blade is taking what I call a bigger bite of air than the ascending propeller blade. It has that greater angle of attack. Remember, our propeller is simply just a wing. It's creating, it has that critical angle of attack. P factor is one of our 4 left turning tendencies. Here's another one. Torque factor, which is essentially Newton's third law. For every action, there is an equal and opposite reaction. Look at this footage we captured at the Cedar Key Airport. If I apply full power instantaneously, and I don't apply any right rudder, well, where does 23 Mike Zulu end up? It doesn't end up where we want it to go, right? But when I have that proper amount of right rudder pressure, we're able to fly out smoothly here. What causes that? Well, when I'm sitting in the cockpit, my propeller turns in which direction? Right? It's turning clockwise in relation to how the pilot is actually viewing it. So if for every action there's an equal but opposite reaction, where is that actually felt? If it's spinning to the right, it's felt and it's going to torque me to the left-hand side. So the moment I get full power in there for takeoff and I instantly get pulled over to the left like you saw here, that's actually torque factor, which is one of our 4 left-turning tendencies, which is pulling us to the left. Once we actually get flying, we interact with some other types of left-turning tendencies, P factor, the previous being one of them, and another one here, which is a little bit tough to understand, and that is gyroscopic precession, which operates on gyroscopes. We know from learning about our vacuum system, operate on 2 principles: rigidity in space and precession. A force applied is felt 90 degrees ahead of the rotation. You don't have to be a physics major to truly understand this, right? If we think of our propeller as a dish, as a gyroscope that's rotating, and I apply a force to that propeller, it's felt 90 degrees ahead in the opposite direction, which also gives us a slight what? Turn to the left. Again, adding to our left turning tendencies. That's probably the most difficult to understand. Let's talk about the easiest to understand now, which is spiraling slipstream. This is the corkscrew pattern. Our propeller, you can kind of see our own wake, we'll call it, coming off of our aircraft, and that slipstream impacts the left side of our aircraft's tail. And when we impact the left side of that aircraft's tail, we push and we yaw which direction? We end up yawing to the left here. You see, we call everything P factor, but in all actuality, P factor is one of 4 types of left-turning tendencies. You don't have to be a physics major to know and understand all of this. What I explained to you is more than suitable for a private pilot level check ride, so don't sweat it. Commercial pilots, we would need to step up that knowledge just a little bit in that case, but certainly this video more than suitable for a private pilot knowledge test and check ride. Listen, I hope you're loving this great M0A.com content. I hope you'll consider us when you're looking for help with that knowledge test, help with that check ride, help with being that safe real-world pilot. Check out m0a.com and our Ground School Academy at groundschoolacademy.com. Enjoy the rest of your day, and most importantly, remember, the good pilot is always learning. Have a great day, guys. We'll see you. Pass your check ride, or I'll pay for it. Join our #1 rated online ground school and participate in live mock check rides and interactive written test prep. Visit groundschoolacademy.com to learn more.